one thing I think you could um, ask in the question and answer. So that without any further ado, please, Duo, the floor is yours.
Oh, thanks, Kardec. Thanks for the invitation and thanks for the nice introduction. Um, my apologize for I have to postpone it from last week to now because I got sick. Um, so can you see my slides? So if I
Yes, but this is
okay.
not the full screen. Yeah, now
Oh,
we can.
yeah. So as Kardec has introduced, I'm from GNS Science, which is a geologic and geophysics institute in New Zealand. So I've been working on using advanced numerical simulation method to investigate the physics of earthquake and slow slope events. So today I'm going to introduce a focus on the Megathrust earthquake, so which means the large scale rupture of Megathrust earthquake and the slow slope. So this work has been in collaboration with a lot of people, with a contribution from a lot of people. And the figure on the right is a is a is a joint rupture from Hikuranki subduction in New Zealand to a crustal fault. And yeah, we because now I'm working mostly on the seismic hazard part. So we want to use some numerical simulation to understand the earthquake hazard on the surface, like ground motion or something. Yeah, but in this talk, I will focus on slow slope. But earthquake is still very important because they're relevant to each other. Um, so some background. The figure on the left is a conceptual plot for the structure and the slope that has been observed in a subduction slab. So from the shallow part to down dip, we can see a change of slip behavior from shallower, like much slow slow rupture that is tsunami generated to the depths around 30 from 20 to 30 kilometer, which is more seismogenic related depths. So there we can have a devastating earthquake rupture and nucleation. And below that, because the temperature, because the environmental parameter like the fluid and the temperature changes, so the slab, the fault transfers from brittle to ductile deformation, and that will promote some low frequency earthquake or slow slip events. So it's a continuous spectrum of sleep modes that has been observed from shallow to down depth. And the signal that has been captured on the surface are also different. So the earthquake will generate very disastrous ground shaking. But for slow slope, they don't they don't radiate any seismic signals, so they can be captured only by like GPS or the deformation can also be like explained by, for example, geodetic observation like INSAR. And it's quite important because the subduction deformation will also lead to, besides earthquake, it will also lead to other like tsunami and landslide. So it's quite important to understand what is a favoring condition for earthquake and what can we learn to mitigate a hazard in this part. And another issue for the subduction is for most case we only have land-based observation like the GPS and the seismometer. But we're short of observation from the seaside. We don't know the if we have more like offshore observation like stations, we can get a better understanding of the whole picture. And we also rely on laboratory experiments to understand the deformation. yeah, in a better way. So that is a slope or the observation related to subduction deformation, and there are already some models, some physical explanation for the distribute for this heterogeneous distribution on the subduction. So the figure on the right is another schematic illustration for the very complex fault zone structure. So it can many factors can contribute or dominate the deformation or the deformation along the fault. For example, uh, the rheological change from shallower brittle to the deeper part ductile, that will make the shallow part have the locked and the slope pattern, that will release the accumulated stream in the form of earthquake. But the deeper part is sometimes mostly silent, but it can still like release significant energy through slow slope or tremor. And if we zoom into the fault zone, it's not a pure like a zero thickness plane, but can have a major fracture in the center and some offsite fault and secondary small fractures that may related to, for example, foreshock or aftershocks associated with the main shock. And because the temperature we the temperature also change with depth, so the increase of temperature will also influence the heat energy release in terms of flash heating, that will change the frictional parameter on the fault. So the condition of the environment along the fault zone is a dynamic. It's changed with time, and it's also changed with the fault slope. So in order to have a better understanding of the nucleation and the growth of earthquake, we need an a theoretical model to explain all of this, what the contribution from all of this factor in the model. Yeah, back to the slow slope. So, so this is trying to this slides try to explain the distribution and the relation with a with a subduction environment for slow slope. So figure on the left is we have the for this is a western coast of Canada and the U.S. called Cascadia subduction, where the when the Fuca and Pacific plate subducted beneath the North American. So all the arrows on the is a GPS is a recorded GPS vectors during the slow slope events period. So the um, so the displacement is reversed to the plate convergence direction. So it's to the C side. And if it inverts the slope on the fault, we can see the distribution of the slow slope is more concentrating between a 10 kilometer to 30 kilometer, like what the color shows in the red column of the figure. And it have a quite big variation along the strike. So, and if we see a cross section of the slab, we can see most of the colorful dots shows the appearance of slow slope and the low frequency earthquake at the depth between the locked part, which is above 10 kilometer, and the stable sliding part, which is when the fault became ductile due to the temperature increase. So this is a like largely observed in a lot of young and warm subduction like Cascadia, Japan, New Zealand, and Alaska, and also some crustal fault like San Andreas fault. So So now people, there are some hypotheses that explain the appearance of slow slip. It's mostly related to temperature, fluid, and the frictional transition on the fault. However, there is so far we don't have like a universal explanation of all of the earthquake observed globally. The other um, evidence or other observations that we can use to understand the uh, behavior of slow slip is from laboratory experience. So in the lab, they can do the continuous loading experiments on the rock examples, and then when they record the friction change, like friction coefficient change on the fault, we can see the oscillation behavior, like the figure on the left. So they like after some time of the loading, we can see this quite a periodic oscillation on the slab. And if we change the loading the maximum effect normal stress or the loading speed, the magnitude of this oscillation will change a bit, but this periodical behavior is kind of consistent. This actually can is a good match with with the so-called rate and state friction. So the friction coefficient will increase in the long term in the long period loading in the continuous loading time. The friction coefficient will increase with time. It's like the fault or the rock surface is healing, and when it's above the threshold of the strength of the rock, it will have this rapid reduce from the so-called static friction to the dynamic friction, which is a shadowed area shown in Figure B. And the total change in shear strength is a so-called stress drop, is a kind of consistent, even though the amplitude of each isolation change a little bit. So this is a very kind of a very important finding from the lab that is explain the appearance of slow slope on the natural rocks, and is consistent mostly with the global observation of slow slope in other places. So well, why are we interested in the physics of slow slope? Because when the as we see from the first slide, like the slow slope sometimes like take places next to the seismogenic zone, so it can have a important influence or implications on the nucleation process of earthquake. So here is like conceptual model try to explain the relation between the slow slope or slow fault creeping with the nucleation of earthquake. There is two end member model. One is called cascade, so means like all the all the foreshocks or the small earthquake before the main shock, they are independent event, so they nucleate on the very smaller patch, which have a lower LC. So here the LC represents the key nucleation length. The key nucleation length is a property on the fault, is controlled the by the properties of the fault itself. Like in the it can have different definitions, but they all proportional to the to shear modular and the critical characteristic slip distance of the rock, and reversely related to what is A and B. A and B is the key parameter of in rate and state friction and the effect normal stress. So it's purely dependent by the material itself instead of the of the slope rate of the fault or other dynamic influence. So the and in contrast to the cascade rupture model, the pre-slope model shows that okay, there is some uh, exists a larger nucleation length LC. So within this larger area, the fault strength is lower, but it can nucleate in a larger area. So it will generate this slow creeping slope before earthquake, and this aseismic slope or creeping slope will increase the loading on the other on the like the small patches, and it will promote force the rupture on these small patches, which is fault shock, and then it will lead the final runaway rupture on the earthquake nucleation. And the third model is a combined model of like the fault includes both of the two types in this region. So this shows like this tells us if we can try to observe or capture this fault shock or this aseismic slope with our instrument before the earthquake, it may give us a chance to forecast or predict the coming of the next big event. But but this is all like from theoretical stage. So now this has been like firmly observed in the realistic world. So yeah, so that is some background related with the presentations and that with the presentations I'm going to talk about today. So I will yeah talking about two areas. So the first is the central Mexico, where we can observe both quasi-periodical slow slope and earthquake of magnitude 7.2 that is that is very likely to promoted by the slow slope next to the seismogenic zone. And the next will be the numerical simulation for earthquake that happened in 2021 in Alaska. Both of this work using the simulation to understand the faulting mechanism. So the method we use is we solve the elastodynamic equilibrium equation, which is the force on the force on the fault surface has to be balanced with the strength of the fault surface. So the the when we simulate slow slip, we can ignore the initial effect, which is the acceleration term in the left equation. So we call it quasi-static formation for the earthquake or slow slope. And we use a friction constitutive law, which is from the lab sliding experiments. So the tau means the shear strength is controlled by the effect normal stress, which is a sigma n, and F0 is a constant friction coefficient. V is a slip rate on the fault, and the theta is a contact time or contact history between these two surfaces. It depends on the time and also the slip rate and the critical characteristic slip distance on the fault. So other parameter is A and B, which is a parameter of the fault. So to we'll balance the two equations, and then we can simulate the dynamic involution at each time step. So in the numerical simulation, we project the physical domain into a numerical domain. So we have to make the key parameters like the material rheology, um, the share modular and the how and some other parameters that may affect the temperature and the fluid uh, evolution in the physical domain into some parameters for each element in the numerical domain. So this is the detail. This is more into the detail of the simulation. If you're interested, I'm happy to discuss this later. Um, so so it's very important to validate the numerical simulation to make sure that we have calculated the correct physical variables evolution. So in order to do that, we have this community-driven benchmark project. So we simulate we simulate the same we simulate using the same fault setup and the same parameter to try to reproduce the exactly same result in order to make sure that all the code works correctly. So in this this is a this setup is normally very simple. So we have a planar fault, which is a uh, uh, vertical distribute, and we have this variation of the frictional parameter along with depth, so which is shown by the first figure, and we then we can compare the output, which includes the ground shaking and the time series at the surface observations. So all of these key parameters, key variables can be compared, and the results will be has been published in the paper. So this is to make sure that the numerical model of the earthquake and the slow slip cycles are correctly captured by the code. And in order to understand, in my research, I use two code. So the first is based on boundary integral method, which we ignore the volumetric stress evolution of the entire domain, and we only focus on the deformation on the fault. So the figure on the top shows the triangular meshes on the slab interface for the Cascadia subduction zone. And and the output, which includes the slip rate history, and the shear stress on the fault. We output these these variables, and we use them as an initial condition in another software called CESO, which resolve the elastodynamic equation in the entire domain, and it's that designed for both wave propagation and the dynamic rupture on the fault. Yeah, so the first will be showing what is the results of slow slope cycle simulation look like. So the movie in the movie, the color represents the slope rates on the fault. We can see the PA is a is a station in the Vancouver in the Seattle, and the slope propagate or start very slowly from the down dip and propagate up dip, and then and then have this bilateral propagation to north and east. This is the slope in one sequence. If we look at if we look at the deformation with time, we can have the figure on the left. So the three curve, the green, black, and the red curve represents the slope, the total moment rate that has been observed in at three positions along the fault. So it appears about every 1.5 year. So the peak represents the appearance of each event, and the bottom represents the slow slope period. And the red dots is a record in one station in close to in the Vancouver Island, I think. So it has a similar deformation. So when the in the inter-slow slope events in the inter-slow slope period. The like the station the signal is along the plate convergence, so it keeps moves to the uh, east. And when the event appearance have the reverse displacement to the other direction and release all of the accumulated slope in a very short time. So the x-axis is the same time scale, and we see the recurrence behavior in the simulation is very consistent with observation. Oh, and the magnitude, the total moment of the simulated slow slip about is equivalent to a magnitude 6.5 earthquake. So it's also consistent with what we recorded for the slow slip in this area. So we dig into more details of each episode of slow slip in Cascadia. Um, um, Besides this GPS signal, they also have some like seismic recordings of the low frequency signals, which is called a tremor. The tremor is different from the typical earthquake in the spectrum because only have a it doesn't have any high frequency signal contents. It only have a very low frequency content in the spectrum. So they don't have a clear arrival P wave or S wave. So they cannot really measure the magnitude, but they can have like accounted the number, the total number of tremor and the tremor per hour, tremor activity per hour or per day is a representative of the how active the tremor change with time. So we plot the tremor activity on top of the plot, and we plot the total moment release during one simulated slow slope. The black one is a moment, while the red line is a moment rate. We find like there is a like the change, the acceleration or the increase of this tremor activity is consistent with the increase of the simulated moment release. So in this red shuttle, it is we call it the acceleration phase of the slow slope, which means it have this unstable slope that release the moment very rapidly. So and we when we compare this when we plot this the process of slow slope of each different time period on the map view, we can see the when the moment rate is low, which is the pink dash the pink shuttle represents it represents the the very small slip accumulator at the deeper depths, and the peak in moment release in the short period is the acceleration of rupture on the up dip on the fault. And the last phase is when it deaccelerate in the speed, and the total cumulative slope is very small. So in this comparison we kind of see consistent evolution in the simulated slow slip and the recorded tremor in this area. So this shows that the slow slope, the rupture of slow slope is not linearly. It's have a like a three-stage evolution. In terms of explaining what is a key parameter in the slow slope, in this area we calculate we find the relation between the average slope of each slow slope episode with the dipping angle or the spatial variation of dipping angle. So the black line, oh sorry, the three diamonds represents the amplitude, the length, long strike length, and the cumulative slope of three patches from north to south along the strike, and uh, the blue line is a variation of strike angle, and the red line is a variation of dipping angle. So we can see the maximum cumulative slope appear. It kind of likely appear with a relative flatter and shallow dipping part of the fault, and where the smaller patch is consistent with when the fault dipping angle or the along strike angle change rapidly. And yeah, so this is this has revealed that the geometry of the subduction interface is very important to determine the magnitude and the recurrence period of a recurrence interval of the slow slip event. Um, Also, so as I said, like this study is based on the long-term or slow slope sequence simulation using the open access software that can be found in our GitHub. Yeah, so this is the first stage that we simulate earthquake, the slow slip sequence. And the next step is we want to investigate what is the influence of slow slip on earthquake nucleation. So we use observation from central Mexico. So the figure on the left shows the so-called seismic gap where no major earthquake has been recorded in this gap. But in 2014, there is a long-term large slow slip appear, which is a orange contours shows the cumulative slope of this slow slip. And so this slow slip lasts about half a year or 6 months. During this slow slip, earthquake happens just next to the area of slow slip. So the color from yellow to red shows the distribution of co-seismic slope, and this beach ball is a fork mechanism of this earthquake. So that is a that is the background of our like second work. So we want to investigate what is the influence from this long period from the long slow slope to this earthquake rupture. This area, this is not the only slow slip that has happened there, but from 1990 to 2014, there has been three other long-term slow slip happened in this similar area. So we first simulate the slow slip sequence with a similar method as that I had explained before. So the fault geometry and the fault geometry has been shown in this figure, and it's also have a like a major change from flatter slab into the kind of deeper dipping slab. And the simulated earthquake sequence and the recurrence interval has been shown in the figure on the right. So we can see the flatter part of the on the fault have a longer recurrence interval, which is the size of this blue circle. So the longer, so this x-axis is time and the y-axis is a long strike distance. So we see like in the in the northern part or in the southern part of the model, the slow slope has longer recurrence interval and a larger rupture length. So it means longer magnitude, a larger magnitude. So we compare the recurrence interval and the magnitude with observation. We found the magnitude and the recurrence interval is very good matched with the observation. But it have a very long strike variability. So these have some smaller events to the north. This is can also be explained by the observation. So what is a stress evolution during this long-term slow slip? So we plot. So in the figure on the left, we first plot the a long strike, or the x-axis is a long strike distance, and the y is time. So we plot the first is a slip rate variation with time and the space. We see the so the slope represents the migration speed during the slow slip. We see so this part is the nuclear is shows the hypocenter of the earthquake. It seems like when the slow slip propagate from this side towards to the center of the hypocenter, it's have acceleration in the migrating speed. And we also calculate a stress ratio, which is the ratio between shear stress to the effect normal stress. We see this ratio um, um, have an increase when the rupture front, or when the rupture front of slow slip getting closer to the hypocenter. So here is an increase in the stress ratio. The movie on the right shows um, yeah, the map view of this variation on the fault, and the profile on the right is the hypocenter is denoted by the star, and uh, yeah, so when the slow slope propagate towards to the hypocenter, there is a sudden like increase in the at the hypocenter depth. And we so we our next step is we couple this shear stress increase from the slow slip into the dynamic rupture simulation. I will skip the details of the simulation, but show the results directly. So the figure shows the slope rate and the cumulative slope on the coseismic slope on the fault. So we see the rupture. We found that the shear stress increase during the contributed from the slow slope at depth is big enough to trigger the coseismic slope because it gave like a shock in the shear stress at the hypocenter. So it's a promote the dynamic rupture on the fault. Um, we compare however, this earthquake, because this area doesn't have a good station coverage on the surface, so we don't have a real good observation or inversion to compel constrain the source model of the earthquake. So we put the source model of two study with either geodetic inversion or teleseismic inversion. We see the hypocenter is a red star. We see the source model are very different because the geodetic is the geodetic inversion always gave a very widespread and slow amplitude, a small amplitude for the coseismic slope, while the teleseismic inversion have a quite a small rupture area but very high slope. And this is the right one is our simulation. We kind of sit in between, so we gave a source model that is looks much larger than the teleseismic one, but smaller than the geodetic one. And the magnitude is also comparable with the teleseismic one. So this is not a perfect example to study the relation between slow slope and earthquake, but um, but this so far is the best effort that we can have. Yeah, here is more observation or comparison with the data. So the moment release is a the black line, and the black dot line is from USGS and or from the paper year 2016 or the SCARDEC rupture source model website. So our moment release is kind of similar with the two peak in the moment release, and we also compare with the GPS vector on the surface. Yeah, so the temporal evolution of shear stress and the shear stressing rate also suggests that there is a significant increase in both shear stress and the shear stressing rate before the nucleation, before the hypocenter. and before the earthquake. So this is a yeah, this is the story of this earthquake. Yeah. So the next one is yeah, I want to talk about our latest work on the on another earthquake that is 2021 in Alaska. This is also a very interesting part because we see from the figure we can see there are several seismic or earthquake segments along the strike. So from the west to east, they have ruptured in history, um, except for except for the so-called Semidi or and the Shumajin segments. So there is no major earthquake happened, no larger earthquake, no larger earthquake than magnitude 8 happened in before. But in 2021, there is a magnitude 8.2 happens in the quite along the quite deeper part of the fault. It's nucleated from 35 kilometer and rupture uh, between 20 kilometer to 40 kilometer. So it's really a deep, very deep rupture. We want to investigate what what is the faulting mechanism for this deep rupture and how it will imply for seismic and tsunami hazard in this area. So we make a yeah we make a yes we make a theoretical model. So we use the information we use um, besides the because there are some preliminary seismic imaging for the subduction interface. They found that in this segment, the subduction sediment layer is quite thick compared to the other part. So we so when the sediment when the sediment layer is more is thicker, it means the structure of that sediment is different is different from the typical fault zone. It may have more fractures and more fluid, and so we it might involve more complex thermal hydro and thermal evolution in this part. So that's why we besides the friction, so we first assume the the fault locking pattern from a slope deficit model. So this is the color indicates which part of the which area of the fault is more firmly locked compared to the other part. And this is constrained by geodetic inversion. And we also consider complex fault heterogeneity, which have this the shape as have these three zones. In zone A, it have a higher it have a like a larger hydraulic diffusivity and a smaller shear zone distance. It will promote faster evolution of temperature and fluid. But outside in zone B and zone C, it have reduced these two parameter. So we want to test if this is if like conceptual model like this could explain the deeper rupture in this area. So we simulate the rupture and we monitor the temperature and the fluid evolution along the strike. So A, B, C is we pick 3 point from the three zones we show in this one, and we found like the zone A has a because the parameter is have a the parameter setup is different, so his have a larger temperature increase and a higher fluid increase. So the fluid pore pressure increase will reduce the strength of the fault. So it promotes the nucleation and runaway rupture in this area. But outside of this zone A, in zone B and zone C, the increase of temperature and the fluid change is much smaller, but still it have a little bit change. So all of this can explain can contribute the rupture along the along this very deep part of fault. So and we plot the slope rate and the cumulative slope with a comparison of other study. So the counter the figure in the movie in the center, we show the slope fault slope with time, and the contours, the black contours, is a result from the joint inversion of the another paper of this Elliott et al. 2022. And we compare the moment when we compare the moment release with other moment rate release with other study, we found that okay, we have the different studies shows like there are multiple peaks in this moment release, means like means this process is it's very heterogeneity, and it experiences several acceleration and deceleration in the slip. But our study is this red or brown line? Is this brown line? We kind of capture the first peak in this or the main peak, which is the deeper part of the center of the central slope patch, and our second peak is quite small compare with the others. So either we needed to increase the we need to introduce another slope patch in the shallower depths as a rupture migrate from west to east, or the geometry or the other parameter in this part is not correctly captured. But we didn't try to improve it because the observation also have a large very large variation or uncertainty in this part. So instead of explore a better model, we compare the surface deformation with a GPS vector and the 1 Hz GNS time series. We find that the amplitude or the overall amplitude at the surface stations are quite comparable with the data, and the time series also capture the main characteristic, except for the vertical part, because the vertical part is of GPS is always more noisy. And yeah, so we as this earthquake have a minor tsunami warning in this area, we output the surface deformation from our simulation and put it into a tsunami simulation for this area. So we use this geocloud, which read the time-dependent surface deformation, the vertical surface deformation from the earthquake simulation, and then simulate the tsunami wave from time zero. So the movie on the left shows the propagation of the tsunami wave, and we pick two stations. One is tidal gauge in the coastal area, and one is open sea dot station, which is a blue dot. So we compare. So the black line is records, and the colorful lines. We chose three models with a little bit difference in the magnitude and the slope distribution. But we see the tsunami simulations, they're almost the same, and and this is for the dot station. We kind of capture the first peak and the arrival of the first peak and the amplitude of this one. In especially the long period wave, but we cannot capture the very short period, the shorter period tsunami wave. We think we need to, in order to do that, we probably need to improve uh the shallow part of the shallow part of the in our simulation. because the seafloor topography is maybe not the data maybe not that good in order to simulate the tsunami. Uh, so at the end, with this simulation, we try to build a conceptual model to explain the relation between slow slope and the earthquake patch and the surface deformation. So this is a conceptual model shows the historical rupture patch, including the 2021 and the 2020 is a rupture of a magnitude 7.8 next to this one, and the difference of the rupture in these two segments is mainly due to the structure of the fault zone, the structure of the sediment layer different. In the 2021, the Semidi, or the western part of the Semidi segment, it have more the porosity or the hydraulic structure of this sediment layer is more favoring the evolution of temperature and the pore fluid pressure. So this pore fluid pressure change during the seismic period, kind of further weakening the fault and promotes the depth rupture. And but the rupture the fault the rupture the area of this rupture is also consistent with a slip deficit that is constrained by the long-term surface GPS inversion. So to estimate the further like seismic hazard, we need to consider both the long-term geodetic feature on the fault and also the small scale structure of the sediment layer or the fault zone, in order to have a better result of the of the potential earthquake magnitude in the future. Yeah, so that's it. This is a summary. So we build a physics-based numerical simulation for both slow slope cycles and the earthquake. For the we find the source of slow slope is related to the structure of the slab. In our study, it's more influenced by the geometry, the dipping angle, and the along strike variation. And we also we couple the slow slope with a dynamic rupture, and we kind of explain the triggering from slow slope to the earthquake. And yeah, when we use a dynamic rupture that couple the more complex physics process, we can explain the deep nucleation and the rupture for the 2021 Alaska earthquake. Yeah, so to better understand the earthquake on the subduction fault, we need as more as information about the structure of the slab as possible. Yeah, that's it. Thanks for your attention. Um, yeah, I'm happy to have any questions.
Great. Thank you very much, Duo. It was a very interesting talk. Definitely, I think there are several people who want to ask if you don't understand the presentation, you can ask, or if you have any question related to general overview of slow sleep event or SSE, please don't hesitate to raise your hands and open your mic. Is there any questions from the audience? So if not, I have a question. quite a list of question actually. Um, so it's a very interesting talk, especially if you are talking about the Cascadia case. It seems that at the king of the subduction zone, you have more um, uh, sleep or moment release, if I am not mistaken. Um, so my question is, does this slow sleep event only occur at the specific conditions along the slab, or it can occur at any subduction zones, or it is more related to the material of the slab or the plate rate or something like that?
You mean this figure?
Yeah,
Like
yeah.
the yeah. Yeah, it's a good question. Um I think in because we didn't include any other heterogeneity in this or other complexity in this in this study. For example, we assume the shear modular is uniform along strike and with down depth, and the only difference is all the is a geometry. For the geometry will in fact it will influence the stress accumulate on the fault during the long-term loading. But yeah, but so for this part, I think the for at least for the Cascadia subduction, it's likely that the geometry, the change of the dipping angle along strike is a major impact on the slow slip. But yeah, but because yeah, this for the other like subduction, when the material can be different and it might have um, need to consider more like other yeah other effect like the geometry like if you have a cement or a quite sharp change in the material on the slab. Yeah, yeah, it's a good point, I think.
So yeah, I'm triggering this question because in Indonesia we have the change of the king of the slab
Mm,
from Sumatra subduction zone to Java subduction zone. It's not only
mm,
the change in terms of geometry, in terms of the king, but also its change in terms of the dip. So in the Sumatra
mm.
subduction zone, we have more shallower dipping zone, and then as it goes to the Java subduction zone, it becomes quite deeper dip. So I wonder, and then we also not observing many a big earthquake in that kink. So yeah, that's why I
Mm.
wonder perhaps it could be related to the slow slip event, or it's become a seismic there.
Oh yeah,
Oh, yeah,
like
I have. Yeah. So the plate rate is not really affecting the slow slip event,
uh well
or if
yeah
you,
I in
meaning that if you have larger plate rate, you will be more having a slow slip event, or
um
the other way around.
oh yeah, it's well in theoretically, if you have a like a higher, yeah, a larger convergent rate, like what's the I think is theoretically it will change the recurrence of the for example, like the from the lab experiments, they found if they like have a higher loading rate, so that mimic the larger plate convergence rate, um it will yeah like change the make the recurrence interval much smaller like you need a shorter time to nucleate the same magnitude of slope on the fault. So yeah, it will I think but in this because in this study we only consider the constant the plate convergence rate is uniform everywhere. But I think yeah, I saw there are other studies they if they have a longer um, yeah, have a longer slab interface, so the plate convergence rate will change significant along the streak. It will, yeah, it will change the slope behavior.
Okay. But uh, if we want to look for a noun as is as SE or slow slip event. So the higher convergence rate will not telling you that this area will be prone to having slow slip event and the other area not. It's not like that, right?
Uh, yeah, so far there is no clear relation. Like it's between the slope, yeah, between the slow slope and the or the magnitude of slow slope and the plate convergence rate. Um, because yeah, because I think it depends on the mostly to the like the temperature or the pore fluid condition on that part if it can have slow slope or not. It's not just uh, related to the plate convergence rate, but it's more related to, for example, the depth of the slow slope or the temperature at that depth. Because most of these slow slopes they were observed in the young and warm subduction, means like the the subduction dipping angle is shallower and the temperature at that depth, like the temperature at 30 kilometer depth is much higher than the cold and the old subduction. So they can have they can have the dehydration like very quickly, and the dehydration will increase the fluid pressure a lot, and that will promote slow slope. So yeah, I think yeah, compared to the temperature and the fluid condition, the plate convergence rate will be a minor factor.
Okay, thanks. Now we have a question from our paleoseismology expert, Pak
Mhm.
Mudrik. Go on, Pak
Hello,
Mudrik. Yeah.
hello. Can you hear
Hello.
me?
Yeah.
I do. It's very nice presentation. Thank you very much. It's a lot of new information for me, and then it's very good presentations. Thank you very much. I have
Thanks.
one questions. In your model, there is must be a lot of simplifications
Mm.
of your activity. So I just have one questions. What kinds information from geology to improve your model?
Oh, it's yeah, it's a very good question and a very yeah, yeah, broaden. Yeah, there is I think there are a lot of things that we can improve. Or we like we need a lot of geological information to improve the simulation. For example, the like like now we actually we didn't consider any the topography in the simulation or the change of the types of rock that could change along strike or along down depth. We assume everything we assume like everywhere in this model is homogeneous, like they have the same like unified geologic unit. But in realistic, it's can yeah, it should be more complex than that. And yeah, and I think the fault and even we have the curvature of the slab interface considered in the model, but the slab is like pure, is smooth, like it's a very smooth fault. So we didn't consider any, for example, the small scale fault roughness on the fault. And yeah, so we cannot really explain the very details of the slow slope. Like it may yeah, if we have more like geological heterogeneous on the fault, we can see some difference in terms of the slope or the recurrence interval, or more yeah, more variation in the recurrence interval in the magnitude. But so far we just focus on the yeah, on the very large scale. Yeah, does this
Yes.
answer your question?
Yeah. Yes. Thank you for your answer, and that's also not easy for geologists to get data that you need because we need a drilling a lot of it is quite impossible and also very deep locations. Yes, but thank you for your explanation.
Yeah, thanks for the question.
So great. Is there any question from the audience? Um, If not, I have another question. So the problem now, especially if the slab interface is quite far from the island, like what we have in Java. So now we have another new technology
Mm-hmm.
like distributed acoustic sensing, like DAS. So
Mm-hmm.
we can like
Mm-hmm.
implement this dust offshore and then put this along the subduction slab. Do you think that this a new technology could also enhance the ability for detecting or confirming the slow slip event that might be useful later on for the simulation and then to expect for a very big earthquake or megathrust earthquake?
Oh, yeah, that's a really good question. I think so. Yeah, so far, I think there. Yeah, I saw some work. They have this ocean bottom dust optical fabric and deployed along the ocean bottom to try to capture the signal. Yeah, if you have that deploy like from the trench to the coast, you can once there is a slow slope like larger enough, maybe magnitude 6 or magnitude 5, because the magnitude 6 slow slip will generate the surface displacement will about like I think 10 centimeter. It's not quite big because it's very deep, maybe 10 centimeter. So I guess if the sensitivity or the resolution of the dust signal is high enough, you can capture yeah, you can really capture the signal, and because you have a very dense sampling along the fabric, then you can very good resolve the extents the along down depth extents or along strike extents of the slow slope, and then you can analyze the data. Yeah, I think you can. Yeah, I think the New Zealand, because New Zealand is trying to deploy another one this optical fabric along the like in between the North Island and the South Island. But they are more interested in using it for tsunami early warning. For example, if you have a tsunami generated from the like far away from the coast, but the signal on the ocean bottom may come faster than the tsunami wave, so it gives you time to a response to that to that like later tsunami hazard. I think that is quite yeah
Yeah.
it is a great like it's a great technique to
Yeah, I think
um
certainly the this new technology could enhance either way the
yeah
early warning and also for the slow sleep event studies and I don't know more subduction zone studies.
yeah
Is there any question from the audience? If not, join me to thank Duo for a very interesting presentation and give us new knowledge today. So I'm sure that there are plenty of new knowledge for us. Yeah, this is the certificate
oh
for you, Duo.
oh
So I
yeah
will
very
send.
thank you it's
So
yeah it looks good
I will also send you by email the
okay yeah
software of this. So thank you for joining us, and then we are looking forward for the research collaboration later on with
yeah
ITS.
yeah
Uh,
yeah yeah thank you yeah thank you for having me there yeah it's a really nice discussion
yeah.
yeah
And then thank you also all for the audience for joining this international guest lecture. So we will have several upcoming international guest lecture also in the future. But stay tuned with the ITS social media and also email. So thank you once again, Duo, and thank you for the all participant. Thank you, Pak Mudrik, and then all the participants. Um,
yeah
and
thanks for everyone for coming yeah
and so So have a nice day, and then have a good weekend there, Duo.
Oh,
In
yeah, you too. Have a good holiday in Indonesia. And yeah, you too. Have a nice day in Zurich. See you soon.
Okay.
Bye.
Okay, thank you. Bye bye. Thank you, everyone.
Bye.
Bye. Okay.